Welcome. You are watching lecture series on electromagnetic field theory. This is lecture number 4, part 2, energy and power. So in the part 1, we have already covered these many topics and we have derived the equation of conservation of power in part 1. In part 2, we are going to cover the conservation of complex power. Okay. So let us see what we have already covered in part 1. In part 1 we have defined the Poynting vector S is equals to E cross H. The divergence of the Poynting vector E cross H is equals to density of power flux. We have defined half epsilon E square as WE, which is electric energy density, and half mu H square as WM, which is magnetic energy density, and sigma E square as density of dissipated power, and negative of E dot Ji plus H dot Mi as density of power supplied. And we have finally reached to an equation of conservation of power which looks something like this, where this PS is the total power supplied is equals to the total power flux plus the total energy stored plus the total dissipated power. Okay, alright. So in this part we are going to derive the equation for conservation of complex power. So what is the main difference? So in the first part we know that S bar, which is the Poynting vector, is equals to E cross H conjugate. So we dealt with the instantaneous field quantities. That is why we used the scripted letters for E, H and S. This time we are going to use the complex power, so we will use the complex field quantities and we will denote it with S is equals to E cross H conjugate. So we can relate the instantaneous Poynting vector S bar with the complex Poynting vector S by the relation real part of S, real part of E cross H conjugate. Okay, now using the vector quantity which we already know that del dot A cross B is equals to B dot del cross A minus A dot del cross B. This is the vector quantity which we already know from lecture number 4 part 1. So here what we are going to do, we will replace A vector, all these are vector quantities. So we will replace A vector with E and we will replace vector B with H conjugate. Okay, therefore we will get del dot E cross H conjugate is equals to H conjugate dot del cross E minus E dot del cross H conjugate. Let's call this equation number 1. Now exactly what we did in lecture number 4 part 1, we are going to use the current concepts, which is we know that del cross E is equals to negative of M total and del cross H is equals to J total. Now if you watch here carefully, this del dot E has been multiplied with H conjugate and here we have a del cross H conjugate. Therefore we are going to make this as H conjugate and this also as J total conjugate, and we will do scalar multiplication, scalar multiply with H star, and we will do scalar multiply with E. Okay, did you see the difference? Here we are doing the scalar multiplication with H star and here we are doing scalar multiplication with E, and we have used H star here and J total star here. Alright, so the star represents the conjugate of that vector, the complex conjugate of that vector. Alright, now When we do this, what we will get? We will get H conjugate dot del cross E is equals to negative of H conjugate dot M total, and here we will get E dot del cross H conjugate is equals to E dot J total conjugate. Hence our equation 1 will become del dot E cross H conjugate plus E dot J total conjugate plus H conjugate dot M total is equals to 0. Let's call this equation number 1. So what we have done is that we have simply substituted this and this over here, and we have brought those two terms to the left hand side of equation 1. Hence we have got this as equation number 2. Alright. Okay. Now let's move forward. Now we know that J total is equals to Y cap E, which is equals to sigma plus J omega epsilon times E. Now if we include the source term also, we should include Ji. Similarly, M total is equals to Z cap H, which is equals to J omega mu H. Again I am including the source term, which is Mi. Now if you see here, we need J total conjugate to multiply it with E. Similarly, we need to multiply M total with H conjugate. So that is what we are going to do. So I will multiply E with J total conjugate, which is equals to E times J total conjugate is sigma minus J omega epsilon E conjugate plus Ji conjugate. Okay, do you understand this? This E remains as it is, and we take the complex conjugate of this part, which is this plus becomes a negative here, this E becomes E conjugate, and this Ji becomes Ji conjugate. Now if you simply multiply it, you will get sigma E into E conjugate minus J omega epsilon E dot E conjugate plus E dot Ji conjugate, which is nothing but sigma mod of E square minus J omega epsilon mod of E square plus E dot Ji conjugate. Okay, let's call this equation A. So this is our E dot J total conjugate. Okay, now similarly we will multiply H conjugate with M total. So H conjugate remains as it is, and we multiply it with J omega mu H plus H conjugate times Mi. Now we expand this and we will get J omega mu H mod of H whole square plus H conjugate times Mi. Let's call this equation number B. So this is our H conjugate dot M total. Okay, now we will put A and B in equation number 2. So what was our equation number 2? This was our equation number 2. So we are going to put E dot J total conjugate and H conjugate dot M total from equation A and B over here. Okay, so let's do that. So we have del dot E cross H conjugate plus sigma mod of E square minus j omega epsilon mod of E square plus j omega mu mod of H square plus E dot J I conjugate plus H star dot Mi is equals to 0. Now we know that E cross H conjugate is nothing but the complex Poynting vector S. So we can replace that as well, and we will get del dot S plus sigma mod of E square minus j omega becomes common, and mu mod of H whole square minus epsilon mod of E whole square is equals to negative of E dot J I conjugate plus H conjugate dot Mi. Now we will hold on to this equation and we will go back to the definition of electric and magnetic energy densities and the density of power flux, density of power supplied, and the density of power dissipated, so that everything becomes crystal clear. So we know that We was 1 by 2 epsilon E square. So in terms of the complex quantities, we will name it as We bar, and this becomes half epsilon mod of E whole square. Okay, this is the first definition. Second definition is, we already knew that Wm is equals to half mu H square, which was in terms of instantaneous field quantities, but in terms of complex field quantities, we will name it as Wm bar, which is equals to half mu mod of H whole square. And the third definition will be del dot S is equals to Pf bar, and the fourth definition is Ps is equals to negative of E dot Ji conjugate plus H conjugate dot Mi, and the fifth definition will be Pd bar is equals to sigma mod of E whole square. So notice I have used the bar notation for the complex quantities here. Okay, so that we can distinguish well with when we compare it with the instantaneous complex with the instantaneous conservation of power equation. All right. Okay, so now we are going to substitute back these definitions into this particular equation, and we will get del dot S plus Pd bar plus j omega 2 Wm bar minus 2 We bar is equals to Ps bar. Okay, did you get that? Why these two terms comes extra? Because here we have mu times H square. So here you have mu times H square. So this 2 comes over here and it becomes a 2 extra factor. That is why this 2 comes extra in this equation. So let me rewrite this equation once more time. So I am going to write this as Pf bar. So I am substituting Pf in place of divergence of S. So this has been replaced with this. Okay, so I am writing it as Pf bar plus Pd bar plus 2j omega Wm bar minus We bar is equals to Ps bar. So here if you notice, this is density of power flux. This is density of power dissipated, and this is stored energy density. Stored energy density, and this is density of supplied power. Okay, so now I am going to name this as equation number 3 and this as equation number 4, and I am going to use equation 3 and apply divergence theorem. Why equation 3? Because in equation number 3 we have a divergence term here. That is why we can apply the divergence theorem. So what I will do is I will do volume integration on both sides, and then I will apply the divergence theorem. So triple volume integration of del dot S dot d tau plus triple volume integration of Pd bar dot d tau plus 2j omega triple volume integration of Wm bar dot d tau minus triple volume integration of We bar dot d tau is equals to triple volume integration of Ps bar dot d tau. Okay, now we are going to apply divergence theorem only in this term. Okay, why only in this term? Because only in this term we have this del operator. We do not have the del operator in here or here or here or here. Okay, that is why we are applying divergence theorem only in this term. Let's apply that. So we will get closed surface integration of S dot ds plus capital Pd bar plus 2j omega capital M bar minus capital E bar is equals to capital Ps bar. Let's call this equation number 5. Now if I replace this term with the total power flux, that is capital Pf, I will get Pf bar, capital Pf bar plus Pd bar plus 2j omega Wm bar minus We bar is equals to Ps bar. So this is total power supplied is equals to total power flux plus total power dissipated or total power lost plus net energy stored. Let's call this as equation number 6. So do get the idea? If you see equation number 4, here we have density of power flux, density of power dissipated, stored energy density, density of supplied power. So the word density is common in equation number 4. Whereas if you compare it with equation number 6, here we have total power flux, total power dissipated, net energy stored and total power supplied. Okay, because when we do the volume integration or surface integration, we will get the total power or the net energy stored in that region. Alright, that is why we convert the density terms into total energy and total power terms. Alright, so this is the right time to compare the equations from lecture number 4 part 1 and part 2. So in part 1 we have derived PS. PS is equals to PF plus d by dt, WE plus WM plus PD, and this was called conservation of power equation for instantaneous fields. And in this lecture number 2 we have derived conservation of power equation as PS bar is equals to PF bar plus 2j omega WM bar minus WE bar plus PD bar, and this we call it as conservation of complex power equation. Now if you notice carefully, there are two basic differences in these two equations. The first difference is this extra 2 term which was not present in this case, and here we have the difference between the two energies, that is WM and WE, and here we had the sum of two energies, that is WE and WM. So these two are the main differences between conservation of power equations when it comes to instantaneous fields and when it comes to complex field quantities. Okay, I hope you have understood this very well. I know this was a very complex derivation. Take your time to digest it for some time and practice some numerical questions as much as you can. I hope you have understood this lecture. Thank you.